Okay, we start out with a quiz. I give you the expression negative b plus or minus the square root of quantity b squared minus 4ac divided by 2a. You should know what to do with that expression, and I usually won't give you that expression. It's one you simply need to know. But for today, I'm giving you the expression. Then we want to solve these three equations. The first one is 2x squared plus 8x plus 8 equals 0. Second is x squared plus 3 equals negative 5x. The third is 2 over x plus x over 3 equals 4. Okay, so if you're in the distance section, you ought to do this as a quiz. Then you can see the solutions. But I would work this. And as a distance student, you're really supposed to be tuning into these videos after they're posted. Of course, if you're getting everything without that, it's fine if you're doing well in your pre-calculus course. But if you're having any troubles, it'd be a good idea to keep up with this course. I'll note that I have a new camera and we're using that camera right now. I can switch back and forth between cameras. This one has the advantage that you can never really see my face. The other one is focused so that you can actually see me and see more of the board. But the other thing about this camera is it's on a tripod that's a little too short. So it's kind of looking up so that there's a little bit of distortion. You can see that whereas this board here is a rectangle, the sides kind of seem to approach each other as you go from bottom to top. And I'll get my hands on a much better tripod and we won't have to worry about that. And it's not a big deal. You're going to be able to see what I'm writing. The other thing is I notice there's some glare right here. And there's a light. So I'm going to have to come up with a way to shade that light. Okay, enough of that. We have the quiz, which I talked about previously. The quadratic formula says this, and there's a logic to it. And we talked about it last time and did some examples. And Open Math also tells you all this, but it doesn't really state the thing as completely as I'd like to state it, which is that the expression ax squared plus bx plus c takes value 0. Is ax squared plus bx plus c equals 0 if and only if x takes one of the values negative b plus or minus the square root of the quantity b squared minus 4ac, all that divided by 2a. this is what the quadratic formula says. It says the only way this can be zero is if x takes one of these values. And if x takes one of these values, then this expression will be zero. Well, we can apply that to the first equation directly. We have 2x squared plus 8x plus 8 and 0. And of course, that matches ax squared plus bx plus c equals 0. Equations match if a is 2, b equals 8, and c equals 8. So the solutions are x equals -8 plus or minus the square root of 8 squared minus 4 times 2 times 8, all divided by 2 times 2, where I've just replaced all the b's by 8. I've replaced the a's here and here by 2, and c by 8. Now, arithmetic is pretty easy. This is going to be -8 plus or minus the square root of 0. All that divided by 4. Of course, you have to do the arithmetic here, but everybody can do that. We need to teach you how to do that. Okay? So that is just -8 over 4, which is -2. Now, ordinarily, there are two solutions, one for the plus and one for the minus. But in this case, it's plus or minus 0. Plus 0 minus 0 makes no difference. You're going to get the same result. If this isn't 0, then you're going to get two solutions. Okay? And I'll even go so far as to say that if you've got a graph of a quadratic function, it's parabolic. It's kind of like this. And what you're finding when you plug the numbers in is the points where y equals 0, which will be on the x-axis. So you'd be finding the x-intercepts. Normally, there'll be two x-intercepts. But if you raise this graph up a little bit, you could get another graph that has about the same shape, but it's only got one x-intercept. That's the case for this function. It has a graph that would look like this. Now, locating where the vertex is, where the axis of symmetry is and stuff like that, well, we're going to get to that very soon in my classes, probably even sooner in other classes. And another possibility is the whole thing is above the x-axis or below the x-axis, okay? In which case, it doesn't cross the x-axis, in which case, you're going to have a negative under the radical, so you're not going to get a real number solution. So the quadratic formula tells you a lot about the graph of a quadratic function. So I'm just kind of foreshadowing that. You're not responsible for knowing that. It's worth thinking about, because then when you get to quadratic functions, you'll have that much of an idea about what's going on. Okay, now, I'm not going to actually solve these two equations, but I'm going to put them both into the necessary form, because neither of these equations is in this form. Okay? It's not ax squared plus bx equals c. It's ax squared plus bx plus c equals 0. Okay, so we've got x squared plus 3 equals negative 5x. Well, we got to have 0 on one side of the equation and everything else on the other side. So we add 5x and we get x squared plus 3 minus 5x equals 0. Now, is it in this form? Well, no, not really. But if you notice that a is a coefficient of x squared, you can identify it. It's just 1 in this case. And b is a coefficient of x, so don't read this as your b. Read this as your b, right? And then c is the number that doesn't have an x on it. So you could use the quadratic formula with an equation in this form, but I don't recommend you do that. I recommend you put it in order of descending exponents so it completely matches the given form. Okay, just a little confusing to look at this and get the numbers right. You could easily think that b was 3 and c was negative 5. Okay, so we put it into this form, so a equals 1, b equals negative 5, and c equals 3. Okay, then I think you're going to get x equals, it's going to be 5/2 plus or minus, you're going to have 25 minus 12, which is 13. And check me on that. I'll put a question mark because I did that all in my head. It's not that much. It's pretty easy to do in your head. So I think it's probably right. I'm not going to check it. Okay. So you go through the whole process. You write it out like this, write out every step, you get a solution. Now, among other things, this tells you that square root of 13 is a perfectly good number. It's between 3 and 4 because the square root of 9 is 3 and the square root of 16 is 4, right? So we can actually estimate maybe that's 3.6 or 3.7 and divide by 2. And we get a number here. It would tell us that our parabola goes through the x-axis at those points, but you don't have to do that part. Sure. Okay, now we've got 2 over x plus x over 3 equals 4. As I've advocated repeatedly, when you have denominators, you multiply both sides by a common denominator. So common denominator is 3x. If we multiply 3x by both sides, we do 3x times the whole side, not just times the 2 over x or the x over 3. It's times both of them. And then 3x times 4. And that gives us 3x times 2 over x plus 3x times x over 3, distributing through. And on the right-hand side, we get 12x. Then, if we want to treat it as a fraction, we have 3x over 1, 3x over 1. The x in the denominator will divide the x in the numerator, and we'll end up with 6. And now the 3 in the denominator will divide the 3 that's in the numerator. We have x times x. That's x squared. And now, even though we can't really see it, unless we've seen a lot of these, can't really see it from here, this is a quadratic equation. Now we put this into standard form. We're going to have x squared. We're going to subtract 12x from both sides. And now we can solve it. Okay. Again, I'm not going to do the step where I don't have room to do it, but just showing you that often you have to rearrange the equation. The other thing is, you can see right away that this has an x squared term, an x term, and a number, right? A constant. And nothing else. So it is a quadratic equation, so you just automatically put it into the standard form and apply the formula. Now, there's another way to solve quadratic equations. Sometimes you can factor, and Open Math shows you that. I'm not going to spend a lot of time. Well, I might spend some time with that. So in this case, it's pretty easy to see you have a quadratic equation. In this case, it's not that easy to see unless you've looked at a lot of these. But you do what I always say is multiply both sides by the common denominator, and out pops a quadratic equation. Whatever your equation is, if it's got denominators, you multiply by a common denominator. Okay? And then that makes the equation much simpler to see and to deal with. You're not dealing with fractions anymore. Okay, so that's about it for the quadratic formula. But I guess I will talk just a little bit about factoring. If, for example, I have the equation x squared plus 7x plus 12 equals 0, then I can write x squared plus 7x plus 12 as x plus 4 multiplied by x plus 3. Now, how do I know it's 4 and 3? Well, these two numbers have to multiply to give you this. Okay? Because when you multiply this out using the distributive law, you're going to have an x times x. Well, that's an x squared. You're going to have an x times 3, which is 3x. You're going to have a 4 times x, which is 4x, and a 4 times 3, which is 12. Now, the 4 times 3 gives you the 12. The 4x that you get by multiplying this 4 by this x and this x by the 3, well, that gives you 4x and 3x, which is 7x. And then x times x is x squared. So we're just using the distributive law backwards. Now, if you come in and tell me that factoring is a big deal and you really have a lot of trouble with it, we'll spend a little more time on it. But it's something we kind of assume you can do. And we assume it, but we know it's not necessarily true. So I'm at least giving you an example. Okay, if we get it in this form, then how is the product of this and this equal to 0? How can it possibly be equal to 0? Well, the only way it can be equal to 0 is if this is 0 or this is 0. That makes sense? Are there any two numbers you can multiply by 0 that are, well, are there any two non-zero numbers that you multiply and get 0? Now, any two non-zero numbers are going to give you something besides 0. So whatever number this is and whatever number this is, one of them's got to be 0. So this splits. X plus 4 equals 0 or x plus 3 equals 0. And I'm not going to go through the steps of solving this. You get x equals -4 or x equals -3. And then you can write your solution set. -4, -3. You know that a graph of this function will go through the x-axis at x equals -4 and -3. I'll repeat that, but we haven't really gotten to that. It's an important idea. Now, quadratic formula always works. It always gives you the solutions. A equals 1, B equals 7, C equals 12. So x is -1 plus or minus the square root of 7 squared minus 4 times 1 times 12. All that over 2 times 1. If you simplify that, 7 squared is 48. 4 times 12 is 40. 7 squared is 49. 4 times 12 is 48. So you get 49 minus 48. This gives you 1. So we could say I can get it in down here because of the camera. This equals I'm going to have to kind of do this. I said -1. I had the 1 here. I just wrote a 1 down there. That was ignorant. It's negative b. It's -7. Okay, I'm not sure you can see all of that. So I'm going to cheat. Prop up this side of the board just a little bit. Now I'm going to live dangerously and prop it up a little higher. Okay, now I think you can see it. The denominator is going to be 2. Numerator is going to be -7 plus or minus 1, square root of 1. Square root of 1, of course, is 1. So -7 plus 1 is -6, and that's over the 2. And -7 minus 1 is -8, and that's over the 2. And you can see that -6 over 2 is just -4. -8 over 2 is -3, and I don't have room to squeeze that in. Okay, make sense? So it works. If you can factor, by all means factor. And if you can't factor, use a quadratic formula. Unless the problem says do this by factor. Then you could actually cheat and use a quadratic formula to find the factors, but you might not think of that. Okay. Now I'm going to let the board go back. Actually, I'd find another domino. Here we go. I can prop this side up. Now that's really dangerous because the dominoes could fall. Then chain reaction might wipe out everybody. Okay. But I'm up here at front and I'll protect you. Fair enough? Okay. All right. Now I mentioned, and let me take a pause just a second, make sure I'm telling you what you need to hear. Okay. This leads us directly to the idea of transformations. Things we've been doing a lot with in my class. And things that, if you're in a different class, you might already be through. But this is an application of transformations to quadratic functions. Okay? Let's just take this function. Let's say f of x is x squared plus 7x plus 12. Y equals 0, f of x equals -3 or -4. So here's my x-axis. I'll use a dotted line because I don't want to put the number up close to the axis. Actually, I'm going to put -3 here and -4 here. These 2 points are on the graph of this function. Graph it's a shifted, maybe stretched, and maybe reflected about the x-axis as well. I didn't mention that, but you get the idea. What do you know about the graph of y equals x squared? Well, just sketching the graph of y equals x squared might look something like this. And you should be familiar enough with your toolkit functions, and especially if you're in my class and you constructed this with an actual construction without using any numbers, okay? You know that this line down the middle is an axis of symmetry. You have the same shape over here reflected over here. Every point over here corresponds to a point over here at equal distance on the other side of the axis of symmetry. So here's a point on a parabola, and here's a point on a parabola. Where's the axis of symmetry? It has to be halfway between. Okay? Axis of symmetry. Got it a little too close to this side, but it's halfway between the x-intercepts. So this line has to be x equals -3.5. That means that the graph is a parabola that goes through these points and has a vertex. The low point is on the axis of symmetry. So maybe the graph looks like this. Now that all should make good sense. Here's your vertex. I use a red dot because that corresponds to what I've done in pre-calculus. It's where the red dot would be if you constructed this and then moved it over. So the vertex, the two zeros are here. Then you'd have to figure out where the vertex is. That makes sense? That's what the quadratic, that's one thing the quadratic formula tells you about the graph of a parabola, the graph of a quadratic function. Okay? It always tells you where the vertex is, incidentally, even if the whole graph is above the x-axis or maybe reflected and upside down below the x-axis and doesn't even go through the x-axis. You still have the axis of symmetry. Okay? And I'm going to explain why, and it's worth understanding what I'm going to tell you. But if you don't, you can still use it. You just kind of memorize the idea. I think it's better if you understand it, so I'm going to explain it. Okay. Your zeros. X equals negative b plus or minus the square root of quantity b squared minus 4ac, all divided by 2a. This is negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. Division distributes through addition or subtraction, just like multiplication does. To justify that, you just say, well, division is just multiplication by a reciprocal. Division by 2a is just same as multiplying by 1 over 2a. So clearly, it has to be this over this, plus or minus this over this. Okay? Now, these are the zeros. Whatever number you get here is going to be added to b over 2a. And then it's going to be subtracted from b over 2a. Now, if you add and then subtract a number from another number, that other number is halfway between the two. Okay? Pick a number. Write it down on your paper. Any number between, let's say between 10 and 100. And then pick another number between 3 and 7. Okay, we're going to call those numbers U and V. So my pick might be U is 49 and V is between 3 and 7. I'll choose 6. Okay. What do I get if I add these two numbers? What do I do if I add V to U? What do I do if I what do I get if I subtract v from u? So do that. U plus v equals what? U minus v equals what? My case would be 49 plus 6, which is 55, and 49 minus 6, which is 43. You have your numbers, right? Have you written them down? Okay. It's easy, right? Probably the easiest thing I've ever asked you to do. Now, this is also easy, but not quite as easy. I'm going to put 49 here. Then I'm going to put 49 plus 6. And then where am I going to put 49 minus 6? So write your numbers here and then show me where 49 minus 6 ought to be. And not 49 minus 6, the u minus v for your numbers. Okay, the point I need to make is that if this is 49 and this is 49 plus 6, then 49 minus 6 will be over here. And 49 is right in the middle. Okay. So if I take any two numbers, add the second number to the first one, and then subtract the second number from the first one, the first number is going to be right halfway between them. Is that obvious? Because everybody drew it that way. Okay. It seems like it's obvious. Well, that works up here, doesn't it? These are the zeros. If this is your U number and this is your V number, after you get done calculating it, this number is going to be right halfway between the plus and the minus, right? So these numbers are your zeros. And this number here is halfway between. The graph is a transformed parabola. It remains a parabola and it remains symmetric about its axis of symmetry, okay? Remains symmetric about a vertical line through its vertex. Put that together. See that this much of the quadratic formula gives you your axis of symmetry. This number is halfway between this number plus this number and this number minus this number. So if you have a quadratic function in general form, identify A, B, and C, use the quadratic formula to find the zeros, and use it to find your axis of symmetry. Well, I'm going to give you this. So once you know the axis of symmetry, how do you find the coordinates of the vertex? You know the axis of symmetry, so what do you know about the coordinates of the vertex? In this case, you know the x-coordinate's 3.5, right? So whenever you have a quadratic function, your quadratic formula hides and it's not all that well hidden. It's kind of right there where you can see it. The x coordinate of your axis of symmetry. To find the y coordinate, you just plug the x coordinate in, and then you have the coordinates of your vertex. To get the y coordinate of the vertex, you just plug in x equals -3.5. You plug in x equals -3.5 up here. Do the arithmetic. You got to get -1/4. I didn't do the arithmetic. I'm actually using what I know about transformations. Okay, so the vertex is at -3.5, f of -3.5. That's -3.5, 1/4, -1/4. In this case, your toolkit squaring function this small picture here has been shifted over to where x equals -3.5. And it has zeros at -4 and -3. So its graph is going to look just like this one. I shouldn't have made those zeros red. I'm going to say red for the vertex. Let me fix that. So the vertex is going to be at -3.5, -1/4. And graph is going to look like this. I'd leave myself room to draw the rest of it. Just take this thing, move it over 3.5 units here and 1/4 of a unit down, and you've got the graph of this function. Now let me go back over that. We look at this function. We write out the quadratic formula. Okay. That's going to give us the zeros. No, I didn't write out the quadratic formula. Actually, yeah, I did. I wrote out the quadratic formula over here. Okay. It gives you the zeros, which are at -4 and -3. Now you could have gotten that by factoring as well. You know the axis of symmetry is halfway between the zeros. you got the zeros by factoring, your axis symmetry will be halfway between the -4 and the -3, right? If you use the quadratic formula, you note that the axis of symmetry is -b over 2a. It's this over this, because this is halfway between the two results you get here. It's -7 over 2 is halfway between your zeros, as it has to be if it's going to be an axis of symmetry, if your graph is going to be symmetric. So you can immediately read off what the axis of symmetry is, and you can immediately see what the zeros are. Then you can find the coordinates of the vertex. They lie on the axis of symmetry, so x has to be whatever the axis of symmetry is. In this case, -3.5. Okay. Camera's low. If I point where I think I ought to point, I block the number. So x equals -3.5. Okay. We can plug then x equals -3.5 in here. I'm telling you that we're going to get -1/4. You can check me. Let me know if I'm wrong. You know, sometimes I make connections and I'm not really careful about it. I'll say something that's wrong. Okay. I'm pretty sure of that. That's a process for using transformations to graph a function. Now, a quadratic function. And that's what we're addressing right now. Okay. Now I'm going to do another one. Y equals f of x equals 3x squared plus 8x plus 12. I don't think that's likely to factor, but because I just kind of picked those numbers up randomly, and if you use random numbers, you probably get something that doesn't factor. But if it does, that's okay, because I'm just going to use a quadratic formula. -8. Minus, I'm thinking ahead to what I'm going to do next. And I need to focus on what I'm doing. Okay. So again, B goes here and here. You got a -4 here. Your A goes here and here. And your C goes here. Before I do anything else, I can tell you something about this graph. The axis of symmetry is that x equals -4/3, -1 1/3. So I'm going to write I'm going to draw the axis of symmetry here. Also, the vertex is on the axis of symmetry. Okay, so what am I going to do? I want to find where the vertex is. I know it's on the axis of symmetry where x is always negative 4/3. So I plug in negative 4/3. I'm going to have to risk everybody's life and raise this board up a little bit. I'll have to adjust that camera later, but it takes a little while to adjust it properly. So I don't want to do it live here. Okay. If I multiply all this out, and I'll do the arithmetic in my head. It's going to be 16/9. You multiply that by 3, it's 16/3. That's 32/3, which gives me 48/3, which is 16. And I add that to 12, and I get 28. Okay. So that's going to be up here somewhere. It's going to be at y equals 28. Well, let's just say y equals 28 here. At this point, we've defined the scale of the graph. Every other number has to be consistent with these. So here's your vertex. Another number we easily find is the y-intercept. Oh, something seriously wrong here. Oh, heck, I messed up. Got to fix that. This is negative 4/3. So this is 16. (16/3) minus 32/3 is negative 16/3. So that makes that 20/3, and that works. Okay. I think my arithmetic is now correct. Okay, so that's no longer y equals 28. It's y equals 6 2/3. What's the y-intercept? It occurs when x equals 0. So y equals 12. Now, what's that tell us about the graph? It tells us that the graph goes through the y-axis at y equals 12. And I'm going to have to extend my y-axis a little bit. Okay, this is 6 2/3. If this is y equals 6 2/3, where is y equals 12? Well, a little less than twice this distance from the axis. If this is 6 2/3, then y equals 12 is probably about here. And here's the y-intercept. It's at the point 0, 12. Well, knowing that, I can sketch perfectly good parabola. I have to have a point over here because of the symmetry. We have the axis of symmetry, so this point has to correspond to a point at an equal distance on the other side of the axis of symmetry, so that the parabola is going to be kind of tall and skinny. And then going to keep getting taller and skinnier. That doesn't really get skinnier, but stay skinny. It's going to keep on going. And there's a graph of okay. Now I haven't used the quadratic formula to find the zeros. Let's just see what happens if I do that. I get -8 plus or minus the square root of 64. Now 4 times 3 is 12. 12 times 12 is 144. It's -8 plus or minus the square root of -80 over 2. It's not a real number. Because of the negative square root of 80. Okay. So there are no x-intercepts. Now, I already knew that just by finding the axis of symmetry and starting that picture, plug the x-coordinate of the axis of symmetry into the function, and I get the y-coordinate. So now I can plot the vertex. It's at -4/3, 6 2/3. I can find the y-intercept because that occurs when x equals 0, so it's really easy to see. The y-intercept has to be 12. The y-intercept is above the vertex, so the parabola can't be a downward parabola. So it's an upward parabola with a vertex above the x-axis. It's not going to go through the x-axis, so you're not going to have x-intercepts. The quadratic formula tells you exactly the same thing about the x-intercepts. You got a negative under the radical. There are no x-intercepts. What happens to the y equals x squared graph? Yeah, I like to say by factor 3. Open Math just says it's been vertically stretched 3, which isn't really a complete sentence, but it leaves out some words and people understand what it means. So I think that's okay, but I can't bring myself. Say it any simpler than that. Okay, vertically stretched by factor 3. And then shifted negative 4/3 units horizontally. Let me go ahead and sketch a there's y equals x squared parabola. Here's the red dot, it's vertex. Vertex has been shifted horizontally, negative 4/3 units. Plus 6 2/3 units vertically. Red dot shifted negative 4/3, up 6 2/3. After this thing has been stretched out by a factor 3 to make it skinnier. Okay. Those are the transformations. Now there's a little more to it than that. Out of time, so I'll just say that this is the connection here with the y equals a f of x minus h plus k. H is your horizontal shift, k is your vertical shift, and a is your vertically stretched factor. A is 3, which is the same as a 3 in front of x squared. So you'll see more about this in the open math assignment. But this is a challenging assignment for pre-calculus students. In my class, I've tried to build up to this idea of vertical shifts and horizontal shifts and so forth. We've been doing it for a month. Okay. And we've talked about the stretching. In other classes, it's been built up to, but you give them the rules. Okay. This is what's going on. This is how you can apply it to a quadratic function. And understanding quadratic functions is a big deal. They're very common. And they're well worth going to a lot of trouble to understand.